This is Math 251, and this is 14.3, Part C. In example 3, we would like to evaluate our circulation integral. Again, multiple ways of writing that, but that's just one of them. Where our vector field f, that is a vector field, is 2xy, comma x squared plus 3. And I'd like to do this for, it says each of the paths shown. My apologies, those did not make it onto your printed copies, so you may want to pause for a moment and draw those on there for yourself. Since I'm using the same vector field for multiple paths, it would make sense that this is going to go a lot faster if instead of parameterizing each path separately, I could discover that this was perhaps conservative, and then I could just use the FTC. If it's not conservative, I will have to parameterize, but here's hoping. So let's start by saying, is F conservative? The test for that is f sub y would have to equal g sub x. Remember, back in the vector field, that's where the f and the g come from. So the derivative of f with respect to y would be 2x. And this g with respect to x is also 2x. So yes, our vector field is conservative. In order to use the FTC, we'll need to find the potential function. So the gradient of phi partial x, and partial phi partial y must equal the f. Looking at the first component, partial of phi with respect to x is equal to 2xy. And doing that integral, phi is integral of 2x would be x squared times the constant y, plus a constant that could depend on y. And then the second component, partial of phi with respect to y, is x squared plus 3. And integrating that, let's see, that's all constant with respect to y, so I'll just get x squared times y plus 3 times y plus a constant that could depend on x. All right, taken together, this tells me that phi is definitely going to have that x squared y term in it, since that's in both versions of phi. And then it looks like c of y must correspond to the 3y. And in this case, the c of x, there's nothing left up here. So in this case, c of x must just be 0. And that's it. That's my phi. All right, well, that's great, because now I should be able to solve these three equations, or these three line integrals very quickly, these circulation integrals. So in part A, I've got a quarter circle going from 2, 0 to 0, 2. Since I already know what phi is, I can say my circulation is phi of the end point, 0, 2, minus phi of the starting point, 2, 0. Plugging into the phi that we found down here, I would have 0 squared times 2 plus 3 times 2 minus 2 squared times 0 plus 3 times 0. And it looks like everything's going to become 0 except for that 6 right there. All right, in part B, we once again want the circulation, and I'm going around my circle of radius 2 the other way, so I'm going 3/4 of the way around, this time going clockwise. But notice, we still have the same starting point. We're still starting at 2, 0, and we still have the same ending point. We're still ending at 0, 2. Therefore, we have this path independence. I'd be setting this up exactly the same way. And phi is just going to end up being 6 again. Don't really have to do any work for that. C, this is a closed path. And since I do have a conservative vector field on a closed path, the circulation is going to be 0. My starting and ending points would be the same, so I'd be subtracting something from itself and getting 0. Notice how much work you've saved yourself in this one in particular. If I had to do this problem by parameterization, I would have 4 separate paths. I'd have to parameterize all 4 of them separately. Calculate the line integral doing f dot r prime dt, and then add the 4 together. So that was a huge time savings in terms of being able to use this FTC. So there's example 3. Let's go ahead and do example 4 as well. We got a 3-dimensional one here. So I'd like to find the work done. Remember, work is calculated the exact same way as circulation, so no difference. I want to move the object from the point 1, 2, 1 to 2, 4, 6. And I'd like to do this in the radial vector field, x, y, z. It wouldn't be all that difficult to do this problem using the traditional parameterization method, but since we're practicing the FTC, let's choose to do it that way. I can only do it that way, of course, if f is conservative. So I need to check that first. And this is one where I do have a little bit of more work to do. It's 3-dimensional, so I have 3 things to check. Let me just jot them down. First of all, f sub y equals g sub x, the same as the 2-dimensional case. But we also have f sub z equals h sub x, and g sub z equals h sub y. We have to check all of those. So here's the f, the g, and the h. F with respect to y is 0. G with respect to x is 0. That one works. Derivative of f with respect to z, that's 0. And h sub x is 0 as well. G sub z is 0. H sub y is also 0. So yes, it looks like this is conservative. I need to find my potential function. So my 3-dimensional gradient has to equal the vector field, which was x, y, z. And let's see, if I set my first components equal, looks like I'm going to get phi is 1/2 x squared. Plus my constant, only x is the variable here, so whoops, my constant could depend on either y or z. Second component, partial of phi with respect to y equals y. So integrating there, phi is 1/2 y squared, plus a constant that could depend on either x or z or both. And finally, the last component, you're probably seeing a pattern here. And phi is 1/2 z squared, plus a constant that could depend on x and y. If I take all 3 of these things together, they actually have nothing explicitly in common. So I'm hoping I'll be able to do just 1/2 x squared plus 1/2 y squared plus 1/2 z squared. I'll talk about one, but I'll leave you to verify the others. Notice the 1/2 x squared could be part of that constant, and it could also be part of that constant. You could make the same argument with the other 2. So I'm going to write phi as 1/2, and I'm going to actually factor out the 1/2 x squared plus y squared plus z squared. All right, now that I've got my potential function, the work, which is the same as the circulation integral, is just phi of the end point, 246, minus phi of the starting point, 121. And that's going to be 1/2 of 2 squared plus 4 squared plus 6 squared minus 1/2 of 1 squared plus 2 squared plus 1 squared. And doing a little bit of arithmetic there, that came out to 25. So Newton meters, foot pounds, whatever the units happen to be for your work. All right, that actually brings us to the end of our fundamental theorem for the circulation or work integrals. So I'm going to pause there, and then we'll save the next video to do the second form of the FTC.